Hello and welcome to the short paper presentation Interactive Finite Element Model of Needle Insertion and Laceration. I'm Pedro Perrusi and I'll present you our work today. Here is a short summary of the presentation I'm about to give. I'll start right away with the context. The motivation to propose a computer graphics model for tissue damage comes from our research in robotic needle insertions driven by biomechanical simulation. The video shows a liver biopsy on a breathing patient model carried out by a robotic arm. In a closer look, we can see the respiratory movement induces high stress along the needle shaft, which can cause the tissue damage. To avoid this issue, surgeons usually perform this operation under patient apnea, which limits the duration of the procedure. Even then, they can feel the tension in their hands and adjust their grip. In robotic operations, this remains a challenge, since there is a rigid couple between the robot and the needle. In this context, cutting models must be integrated into the simulations for our control framework to account for this behavior. Computer graphics literature is vast in the simulation of cut and topological changes. The state-of-the-art methods may be classified into three classes: mesh-based methods, meshless methods, and hybrid methods. The simplest of the mesh-based methods is to delete elements along the cutting path. It's also possible to split them in two around the cutting path. Both of these strategies, however, change the mesh volume and can induce instabilities into the simulation. Local remeshing can mitigate this effect, however, it might still induce U-shaped topologies. Meshless methods tend to use particles and their interactions to simulate cut. They tend to be faster when compared to mesh-based methods, however they still lack of consistent geometry for collision detection after the cut. Hybrid methods tend to combine meshed surfaces and particles to simulate cutting. An interesting property is that they can present independent cut surface geometry. They also tend to combine the advantages of both mesh-based methods and meshless methods. Throughout this work, we'll be presenting an hybrid approach to simulate cut and laceration in needle insertion. It's important to mention a cutting model for needle insertion has already been proposed. It is a mesh-based method which relies on non-conforming meshes to simulate the cut. It does still raise stability issues in an interactive context, and also they use a geometric criteria to initiate the cut. While on our side, we intend to use those very same lateral forces we see on the plot as a mechanical criteria to initiate the cut. Before introducing our method, we'll take a step back and review the interaction model used in our simulations. It's based on Lagrange constraints expressed in the equation below, where W is the shear complement of the system and embody both the mechanical state of each body and the constraints linking them. Lambda are the reaction forces to any violation of the constraints, and sigma free is the free motion interpenetration computed between the bodies. We solve for both lambda and sigma using an implicit integration scheme based on the SOFA framework. We built our method as an extension to a previous needle insertion model. When the needle is outside the tissue, a contact constraints react to the collision of its tip and the tissue surface. There is also a friction constraint to resist the motion of the needle when sliding through the tissue surface. After the punction, the needle will be constrained to follow only the insertion direction by two bilateral constraints per needle node. These constraints resist to any lateral motion, and the lateral coupling force is the one we saw on the plot before. There is also friction to resist the movement of the needle alongside the insertion direction. Our method proposes then to extend the previous needle insertion model to include tissue cutting and laceration. When important lateral forces are measured, a new set of constraints will be introduced. At the level of the entry point, everything stays the same. The needle is allowed only to be inserted into the insertion direction. For the other needle nodes inside the tissue, however, there is only a single bilateral constraint that will be assigned, meaning the needle is free to slide through the cutting plane, while any out-of-plane movement will be resisted. Contact constraints are also introduced between the needle and the cut plane borders. If important contacts are felt, the cut plane will then be extended. Now we'll go to the step-by-step details with an example simulation. The puncture phase is when the needle is still outside the tissue. When the puncture forces overcome a certain threshold, the insertion will begin. When inside the tissue, the bilateral constraint pair on each needle node will resist to any lateral motion. We can see on the plot the rising blue line is the lateral forces resisting to the needle movement, and when they overcome a certain threshold, the cut phase will begin. In the cutting phase, the needle insertion constraints are removed, and a point cloud is created around the needle axis. A new set of constraints is added, allowing the needle to slide through the cutting plane. Finally, the tearing phase is the phase in which the cut plane might be extended. If a contact force superior to a certain threshold is detected, the cut plane will then be extended. We can see in the plot that the green line has sudden peaks when the cut plane is extended. As first results, we'll analyze the performance and stability of our method. The computational times measured achieve an execution rate of around 60 Hz, which is suitable for haptic feedback or robotics applications. In terms of stability, the method performs well for small deformations. We've seen stability problems when the needle moves rapidly and the tissue is already at a deformed state. In a haptic feedback scenario, the needle model performs well. The user can feel the constraint violation forces resisting the needle movement. We can easily drive the simulation to the cutting plane by increasing the lateral forces in the tissue, although the transition can sometimes be way too abrupt. We can also feel the sudden drops of the contact force when extending the cut plane. These forces does not seem realistic for the moment, and this effect might be mitigated in the future by including friction constraint along the cutting plane. We also tested the model in a robotic needle insertion scenario with two different needle stiffnesses. While the rigid needle reaches the tearing threshold, the flexible needle imposes less stress to the tissue and never lacerates. As a conclusion, we present you a novel needle cutting and laceration model, which relies on a mechanical criteria to trigger the cutting phase and the tearing phases. It performs in real time and with stable results in an haptic force feedback scenario and a robotic needle insertion scenario. In future works, we want to integrate friction constraints alongside the cut plane to mitigate the sudden drops in the contact between the needle and the cut plane borders, and also to integrate this model into a robotic control framework, so the system can not only detect tissue damage, but also cope with the different motion inside the cut plane. This work was supported by the French National Research Agency under the project SPERI and the Investissement d'Avenir program. Here are the references for these slides. Thank you so much for your attention, and I hope we can discuss further this work in the Eurographics forum. Thank you and see you later.